Okay, guys, good evening to everyone. Rowena, Kasoji, SR, and Zandile, including Miss Ngwenya. A very good evening to everyone. As we welcome you back here to our sessions, evening sessions. So, yeah, we're just going to recap. I hope we're going to have a good time here as we're about to start. So, but let me announce it that for tonight, you guys won't be having mathematics. Mr. Magaye is not around due to some family responsibilities. There's been death in his family, so he has to attend to those family matters. So for tonight, from now until 8 o'clock, we're going to be having strictly physical sciences, and we won't be having mathematics. Hopefully by Monday, we'll be back, but it will all be communicated on the WhatsApp group as to when exactly will Mr. Magaye be back. So I thought I should put it out there that for those who might be in for maths only, Mr. Magaye is not around to those family responsibilities and the unfortunate situation that has befallen his family. Other than that, I hope we are all good. And for tonight, I think you have seen the message. We're going to be discussing something on electric circuits. Let's just put it out there. Electric circuits, everything concerning electric circuits, including what we have to be covering now at grade 12, which is basically two small concepts yet crucial: internal resistance as well as the EMF of the battery. So that is what we're going to be discussing tonight. And maybe for the next 3 evenings, we shall be discussing that. We'll see how fast, or rather how fast we are making an impact on this one. And then we'll do all the topics that are to be done in this term, that is electric circuit, and that is electrodynamics, and last but not least, electrochemical cells. Those are the 3 topics that are to be covered this term. So we're going to be discussing those. And then after which, then we'll then look at the entire revision program, which will help us to prepare for the, what you call this, trial examinations as well as the final examinations. So with that having said, a very warm welcome to everyone, and let's get started. And to those of you who are meeting me for the first time, my name is Sandile Villane. For now, my equipment is having some technical issues, so that needs to be resolved. Unfortunately, I won't be seeing my face tonight, but I promise you next week, definitely, you shall see the face. All right, let's get started. So like I said, guys, we're going to look at this and then try to make a concept flow from what you have done in grade 10 to exactly what we shall be doing at grade 12. So we'll just summarize that quickly in the next 30 or so minutes. Electric circuits. So want to look at the concept flow. How does the concept flow through across the grades? And this is precisely what we're going to be looking at from grade 10 through to 12. So if you recall very well, at grade 10, we only did parallel and series circuit. This is what you were focusing on at grade 12, parallel and series circuits. And we even have a formal experiment on this one. So when you compare the parallel series circuit, we'll summarize that a bit later. And then we went on to grade 11. At grade 11, we then introduce you to the concept of Ohm's law, where you look at your ohmic and non-ohmic resistors, or rather conductors for that matter. So we look at Ohm's law. And you are also supposed to look at the cost of electricity. Oh, no, before that, cost of electricity, we look at electrical power and electrical energy. And electrical energy. This is what you look at. Then you looked at the cost of electricity. That is what you did in grade 11. Now here we are. This is where you are at now. And then here we only placed the last missing piece of a puzzle, which was a concept of internal resistance, as well as the concept of the EMF of the cell, or a battery for that matter. So this is your whole concept flow and what you are exactly expected. So obviously at grade 12, we expect that you understand all of this. So this is the concept of electric circuit holistically across the grade, from grade 10 through to grade 12. I hope you guys are still with me there. So I'm just hoping that you guys are still with me as we look at this. So let us look at what you discussed in grade 10. It's just gonna be a brief summary. Won't be we're dwelling much on this. So we wanna compare the parallel and series circuit, and we're gonna summarize this. Somehow we may have to do some virtual experiments, but this is what you discussed at grade 10. After performing the experiment, these were the findings about the parallel circuit in as far as current, potential difference, resistance are concerned. So with this, you guys have noted that in a parallel circuit, you might have noted that the potential difference of all the resistors which are connected in parallel is the same. So if you've got 2 or 3 resistors connected in parallel to each other, just know, because this is going to be very important. It's an observation, by the way, guys. This is an observation. Like I said, we may have to accompany that with an experiment. So let me have 2 bulbs connected parallel to one another. Parallel circuit means, so I'm trying to quickly build my circuit. Obviously, a circuit needs a battery. You can't have a circuit without a source of energy. A battery is your source of energy. So it is what is going to feed the energy to this resistor here, or rather to this light bulb that you are seeing there. And obviously, your circuit will need a switch. A circuit must have a switch to control the flow of energy, especially when you don't need the energy. So one of the precautions when you perform these experiments, we normally say to you, keep the switch open if you are not taking any readings. Only close the switch once you are ready to take the readings. Hence, as you can see, I have an open switch there. Let me complete my circuit quickly. And I obviously gonna need a switch there as well. Right, again, I'm not taking any readings. I'm tempted to want to add another switch here. Let's throw this guy away. We don't need you. Let us have another switch here as our main switch. So there you go. I've got 2 resistors which are connected in parallel to one another. And I want to take the reading, so I'll start closing the main switch. Nothing is happening. Let's close the first switch. Oh, there is a current flowing now. And if we close another switch, oh, there is. Both my bulbs are now working. So I'm quite certain that this is working. So I want to now make this observation. I'm performing an experiment. I want to measure the potential difference across the first bulb. The potential difference of the first bulb. And then I'm getting exactly 9 volts. The 2 bulbs are connected parallel to one another, and our expectation, we have said, for the 2 bulbs or resistors which are connected in series, the potential difference is the same. Let us show you by bringing in the second voltmeter. As you can see, 1 voltmeter is connected to bulb 1, the second voltmeter to bulb 2. But I want to make this bulb to be of different resistors. Bulb number 1 is 10 ohms. Let's say we increase this to maybe 12 ohms, or even 16 for that matter. You notice that even after having increased that resistance, Oh no, I've done a mistake. I made a mistake. I didn't want to throw that bulb away. Okay, let's do it again. I want to increase this resistance. It doesn't matter what the resistance of this bulb is. For as long as these bulbs are connected parallel to one another, all I'm noticing is that they are having the same potential difference regardless of the magnitude of the resistance of each of the resistors. So that is my observation as far as the parallel circuit is concerned and the potential difference. Any questions so far? So we are not sucking this out of a thumb. It's an experimental evidence that we are speaking about here. As you can see, this bulb number 2 is of 10 ohm resistor, but bulb number 1, 18 ohm resistance. 18 ohm and 10 ohm resistance connected parallel to one another, their potential difference is going to be exactly the same. Notice that even if I move these terminals to the, even if I move my voltmeter and place it across the terminals of the battery, I think I'm moving the wrong one. I wanted to move this one across the battery because all my resistors are connected. It's a strictly parallel circuit. The potential difference across each resistor is the same as the terminal potential difference. By terminal potential difference, we mean the potential difference across the battery when there is the current flowing. So notice that. And I hope you are making those notes that for parallel circuit, potential difference is the same. What about this one? For a series circuit, we said potential difference is divided. Oh, that's a horrible looking potential. Here, potential difference is shared, which means whatever the battery is going to be supplied, it will be split, or rather it will be shared by each of the resistors which are connected in series with one another. And let us perform an experiment to confirm this. Okay, I'm gonna need to remove this and remove this. Well, I don't know what happened to my bulb. Okay, but I want to connect my bulbs now in series and no longer in parallel. Let's cut this, cut that, throw all of these away. Why am I having so many conductors? Okay. Let's throw you away. Okay, let's have another bulb connected in series with this first bulb. So my second bulb will be here, and there we go, and there we go. But also, okay, there we go. Switch open first. Let's look at this one. Let's look at this one. And then we close the switch. Look at the brightness of these two bulbs. The more you add them, the dimmer they become. But now what we are concerned about is the potential difference. So I want to have 3 voltmeters in this case. 1 voltmeter would measure this potential difference. Okay, it's not connected yet. There you go, 5.79. The second will be connected here. It says 3.21, and I want a third voltmeter. So notice that, okay, now I'm having 2 different readings because the 2 bulbs are of different resistance. This first bulb is 18 ohm resistor. The second bulb is of 10 ohm resistance. And then notice that when I add these two, what do I get? It looks like I get exactly 9 volts. When I add 5.71 and 3.21, that is exactly 9 volts. So I'm expecting that this is the potential difference supplied by the battery. So I'm going to take this and connect it over there across the battery. Now I'm measuring the total potential difference or the terminal potential difference. It's 9. So I'm noticing that for 2 resistors or even more connected in series, they are sharing the total potential difference that is supplied to them. Notice that. And also notice that if I connect this voltmeter across the 2 bulbs, across the terminals of the 2 bulbs, it gives me exactly 9 volts. But if I measure the first one, it's 5,71. If I measure the potential difference of the second bulb, it's 3,21. When you add 5,79 and 3,21, it gives you the total potential difference. So that is what we mean by this. I hope you guys are following me here, because we want you to understand this. Therefore, it is quite imperative that we perform these virtual experiments. And then with this one, the opposite happens. Sorry, not series. With as far as current is concerned, in a parallel circuit, current in the parallel circuit splits or is shared. So this one divides the current in the parallel circuit, whereas in a series circuit, current at any point in a series circuit, current remains the same. We shall look at that quickly. And then let's just take a quick look at that one. Let us perform yet another experiment. So guys, I'm not having a second screen. Should anyone have a question, because I won't be able to notice your hand up, please feel free to just disturb me. Is that fine? Please feel free. If you're having a question, you may just open your mic, unmute your mic, and then start talking. You will be noted, because I don't have a second screen to monitor the hands as well as the chats. So please feel free. Right. Now I want to look at the current. This is a series circuit as it is. Before we disturb it, I want to put here the ammeter that is going to measure the total current. So, oh, this one is, okay, now let me use this ammeter. I want to connect this ammeter so that I am measuring the total current of this from the battery. As you can see, it's 0,32. My resistors are connected in series with one another. So I want to measure the current at this point. One thing that will help. I want to measure the current through this bulb. So I'm going to remove this wire and I'm going to connect another ammeter between these 2 points. As you can see, it's the same as the total current. And I want to place another ammeter at this point. Switch. But I wanted this to go that way. Okay, that's a funny looking circuit, but it will serve our purpose. Close. As you can see, at any point in this series circuit, current is the same. So it's 0,32 before the bulbs, between the bulbs, and after the bulbs. So the current in a series circuit is the same. That is precisely what we meant by this statement here under series. Current remains the same in a series circuit. So this was something that was supposed to be done experimentally, and observations were supposed to be made. Okay. And we want now to connect the 2 bulbs parallel to one another, instead of having them in series. We want to have these bulbs connected parallel to one another. So I'm going to leave this one bulb here. Let me open my switch. And I want to connect this second bulb such that it is parallel to the first one. And then I want to also have an ammeter And I'm going to now complete the circuit by adding the conductors. These are just your conducting wires. And we have a complete circuit. Let's close the switch. 1,40. 1,40 is the total current. And then look at the current through first bulb, 0,50. Through the second bulb, 0,90. And when you add 0,5 and 0,9, it gives you the total current that goes to the battery and from the battery. So 1,40 is your total current. 0,5 is the current through bulb 1. 0,9 is the current through the second bulb. When you add 0,50 and 0,90, it will give you exactly 1,4. And that is what we mean by having a parallel circuit as the current splitter. So it splits the current divider. That is what other books will say. Parallel circuit is a current divider, and that is precisely what they mean. Any questions so far? Any questions so far, guys? No questions. Great, great, great. So I wanted to demonstrate this, and so that we are establishing this concrete knowledge. Now, this is there is an empirical evidence. No one can argue against this because we have made the observations ourselves. We didn't suck it out of our thumbs. And then the other concept, we can look at the total current. What happens when we add more resistors? More resistors we add in parallel. When we add resistors in parallel, this one will increase the total current. And from Ohm's law, if the total current increases, then the total and decrease the total resistance. According to Ohm's law, if the total current increases, then the total resistance will decrease. A very important point to make when we go to answering conceptual questions such as what happens when you remove a particular resistor? A very important point to make and to take note of. And then whereas here the opposite happens here, adding resistors decreases current. And from Ohm's law, the total resistance will increase. Oh, let us also mention that when we remove one bulb, this circuit will continue working. Parallel circuit, when you remove this one resistor in a parallel circuit, this will leave the other resistors azoqhubeka asebenze, will continue functioning. Whereas here, unfortunately, one resistor dies, all the resistors will die because current to flow, we need a complete or the closed path. So here, once you remove one resistor, or if one bulb burns out, then the rest of the circuit will die. And that is what we're going to be looking at. Maybe we can add the fact that to calculate the effective resistance, we normally use them depending on the number of resistors that you're going to be having, 1 over R1 plus 1 over R2. And by the way, guys, this is a mathematical manifestation, which I'm tempted to prove with you. It will depend on how many resistors. This I am tempted to do with you. Remember from point number 2, from bullet number 2, in a series circuit, the current splits. What do we mean by that? We mean to say total current will be equal to I1 plus I2. But since you guys know that, and also remember, potential difference is the same. But since we know that current is equal to V divided by R, I think we should know how to come up with that formula. Current is equal to potential difference divided by the resistance. So if it is the total current, potential difference is the same. It will be the total resistance over there. If it is I1, it will be R1. V is the same. We've already established that a potential difference is the same for all of these things. So that will mean that if I replace all of these I's by V over R, I will have I total as V over R total. So this will be V divided by R total. And I1 will be V divided by R2. And I2 will be V divided by R2, depending on how many resistors you're having. So you'll notice that V can be factored out and you'll be left with this. And here as well, you can factor out this V, which is the same because potential difference is the same for all the resistors which are in parallel. And as you can see, by cancelling out or by dividing this V, you are left with exactly that formula. 1 over R total is equals to 1 over R1 plus 1 over R2. It's a mathematical manifestation. So we interpret this statement mathematically and we come up with this formula. This is how we derive this formula. Not that you need to know it, but we are just proving it to you that it is true. And also here, what is divided or what splits in a series circuit? It is the potential difference that is split. Potential difference is shared. What do we mean by that? We mean to say the total potential difference or the terminal potential difference will be shared depending on how many resistors you're gonna be having. In my example, I'm only considering R1 and R2, but you will remember from the formula that if I want to calculate V, I have to use I times R. Remember, we said in a series circuit, current remains the same. Bullet number 2, current remains the same in bullet number 2. So I is the same, but if I've got V total, then I need to be speaking about R total. V will be the same for all of these resistors which are in series, an observation that we have already made. So here I'm having V total. I'm going to replace V by IR total. V1, IR1. V2, IR2. I is the same for all the resistors in series. Again, I can always factorize I, which is a common factor. It's the same. And this leaves me with this. And when I divide both sides by R, by I, sorry, I've got R total for the series circuit, R1 plus R2, and that is basically what we're gonna be looking at. I don't know if there are any questions so far. Right, looks like we don't have any questions so far. So that's basically what we have done in grade 10. In grade 10, this is precisely what we are expected you to have mastered at grade 10. We move now to grade 11 and we look at your Ohm's law and the ohmic and non-ohmic resistors. So with your Ohm's law establishes a relationship between the current and the potential difference. When the temperature of the conductor...
Just copy the rest of those formulas.
The formulas. Okay, these formulas. Don't worry, I will send this as PDF when you finish. Ne?
Okay, thank you.
Yep, I will share the entire in PDF form. I hope you are in the WhatsApp group. Are you in the WhatsApp group?
No.
You're not. I will need you to drop your WhatsApp number, or what I can do is I can share the link. I will share the link to join the WhatsApp group.
Rowena will send it on our physics group.
Oh, okay. No, Rowena will be of great help. Thank you, Rowena. But I'll also share with you the link to join the WhatsApp group, or Rowena can add you, whichever way. But I'll also share. So to anyone who needs to take notes, please notice that everything that we are doing here, all of this, we are going to share it as PDF. And then to those who are not in the WhatsApp group, please drop your WhatsApp numbers. And then, or I will share the link to the WhatsApp group, then you add yourself to the WhatsApp group. So yeah, please feel free. All right, then we look at Ohm's law. Now we are at grade 11 now. We look at Ohm's law. Ohm's law investigates the relationship between the current and the potential difference of a conductor when the temperature of such a conductor remains constant. And then these were the findings. According to the Ohm's law, it simply says, I'll just summarize it. I'll share the wording of the statement. So because we are summarizing this, current flowing in the circuit is directly proportional to the potential difference. But it doesn't stop there. It says, provided the temperature of a conductor remains constant. So if your conductor obeys this, then we call it an ohmic conductor. We interpreted this mathematically by saying directly proportional means if I plot the graph of current against the potential, or maybe let us do it the other way around, potential difference against the current, we expect to get a straight line graph passing through the origin. This is what we expect to find. And the gradient of such a graph, because a straight line has got a special feature which is called the gradient. And the gradient of a straight line is constant, remember? The gradient of a straight line is a constant. So what we expect to see, Tina, is that the gradient of this set graph, when V is plotted against I, the gradient of this graph will be equal to the resistance of a resistor. So it is important that you notice that if and only if V is plotted against I, V on the y-axis, I on the x-axis, then the gradient of such a graph will be equal to the resistance of the conductor. And that is basically the essence of this. Very important to notice. Very important to notice. And then thereafter, you can look at your ohmic vis-a-vis non-ohmic conductors. That is what to look at. Ohmic, this one obeys Ohm's law. Ohmic conductor or resistor. Non-ohmic conductor or resistor. This one obeys Ohm's law. Whereas this one doesn't obey Ohm's law. And then your examples of this. The examples of your ohmic resistors is your laboratory resistor, your normal resistor. Resistors. Resistors are good examples of these ohmic conductors. Here, your examples involves the light bulbs. Light bulbs, I think we can all agree that when you switch on the light bulb for some time, you will feel that the temperature of the bulbs increases. So temperature doesn't remain the same. Ohm's law is not obeyed. The other examples here will include your light bulbs. You can have also your thermistor. There is what they call thermistor. You can also have your transistor. Those who are doing electronics will know about this, but we'll show you the pictures of how do they look like. Bulbs, thermistor, transistor. Those are some of the devices or conductors which are non-ohmic. your diodes as well. LEDs, light emitting diodes. They are all examples of non-ohmic resist conductors. So these are some of the examples, and that is what we spoke about in grade 11. So I hope you guys are still with me here. We are almost done. We want to rush to quickly cover this so that when it comes to doing the questions, we just cruise with something that we have in our minds and that we have already revised. So this is about your ohmic resistor. Remember Ohm's law, you need to be able to state this statement in words. So I will share the formal definition of this. All the formal definitions, I'm going to send it through. Remember, there is a document called Examination Guidelines. Some of you may have heard it, but we all need to have heard about it. Examination Guidelines. For every subject that you are doing, make sure that you download the Examination Guidelines, because it is exactly that, guidelines towards the examination. You can't sit for an exam without having seen the contents of that document. You can download it for free. Physical Sciences, grade 12, examination guidelines. If you need one, I can also share it with you. Right, so at grade 11, once we are still at grade 11, we then look at electrical power and electrical energy. Electrical power and electrical energy. Ooh, how do we do this? This is how we do it. Remember from grade 12, sorry, grade 10, we defined potential difference as the energy transferred per unit charge. Here, the W work done or energy transferred. Electrical work done. Here, Q stands for the electric charge. So by definition of the potential difference, it is defined as the energy transferred per unit charge. W for energy transferred, work done or energy transferred per unit charge. We also defined the second concept. We defined the current. We said current is the rate of flow of charges, the amount of charges that passes a given point per unit time. So current is defined as Q over delta T, rate of flow of charges. Again, I'm going to share these formal definitions with you. So it is from these two definitions that we're able to come up with the formulas to calculate electrical power as well as electrical energy. But notice this, that if I make this Q the subject of the formula by multiplying both sides by delta T, I'm going to have I times delta T is equals to Q over delta T times delta T. I've multiplied this formula by delta T, both sides. And what I'm ending up with is that Q is equals to I times delta T. Now, if I were to name this as equation 1 and this as equation 2, between these two equations, I've got this common variable, which is Q, and there is Q there. So I can always replace, whenever I see Q, I'm going to substitute or replace Q by I delta T. In the place of Q in equation 1, I'm going to substitute Q by I delta T. So I'm solving these simultaneous equations. I want to substitute equation 2 into equation 1 so that now I'm having V is equals to W over Q. Q is I delta T. Oh, look at that. But you also know from definitions that electric or power in general, average power is equals to work done per unit charge. And I happen to see W over delta T. Whenever I see W over delta T, I can always replace that with power. W over delta T. That's a definition. Power is the rate at which work is done, or power is the rate at which energy is transferred, or the rate at which energy is dissipated. That's a definition of power, average power. So in my case, whenever I see W over delta T, I'm going to replace W over delta T by P, so that I've got V is equals to P divided by I. And when I multiply both sides by I, I've got power equals to V times I. That is the first formula we're going to use to calculate electrical power. So we're playing around with the definitions. 3 definitions to be precise. Definition of a potential difference, definition of electric current, and definition of not electric power, average power. 3 definitions. We came up with this formula. But remember what we have said to you. So that is the first equation to calculate power. But you know that V is equals to I times R. V is equals to I times R. So if I replace this V by I times R, what will manifest? And the answer is I'll have P. In the place of V, I've got IR. This is V multiplied by I. Now I've got I times I, then we've got I squared times R. That is the second formula to calculate the average power. And again, if I say, well, what if I wanted to replace I by V divided by R? I is equals to V divided by R. So if I take this into that formula, into this very first formula, what will I have? Now in the place of I, I'm going to put V divided by R in the place of I. I'm going to replace I by V divided by R, so that I've got power is equals to V times V over R. And that will give me V squared divided by R. That is the third formula to calculate the average power, ladies and gentlemen. Any questions so far? So this is how we came up with these 3 equations to calculate the average power. And obviously, if you multiply all of these 3 equations by delta T, you're gonna get the formulas to calculate electrical energy. You multiply all of this by delta T, you get the formulas to calculate electrical energy. Right. Let's pause and take some few questions. We are nearly there. We are nearly there, ladies and gentlemen. We are nearly there. Now we're going to discuss what we want to talk about. Right. So finally, I think we can now talk about the cost of electricity. Will cover it because it's just a straightforward thing. Those who are doing mathematical literacy, those whom are not here, those who do mathematical literacy, they do what they call tariffs. And that is where they deal with the detailful tariffs, such as cost of electricity, cost of water, and stuff like that. How do you calculate how much you're going to have to calculate at the end of the month for your electricity, for your water? That process, they call it tariffs. But yeah, now we're not doing mathematical literacy, now we do pure mathematics. So at the end of the day, this is where we are at grade 12 now. EMF and internal resistance. Finally, this is just one missing piece of the entire puzzle. So you're not going to be looking at just internal resistance and EMF. You still need to know all of this before you come to this part. Everything that we have covered from grade 10 through to 12, you need to know it. That is why we have to do that brief discussion. So now we want to demonstrate to you the concept of EMF of a cell. How do I clear this out there? Let's start afresh. Now, if you look at this, I'm having a battery here. And then when I go to advance, under advance here, it will give me some information. Wire, tiny resistance, a battery, tiny resistance, battery resistance. Let us give it a meaningful value. Let's give it just a value. It matters not what this resistance is. But now you can see our battery, we have given, it initially had no resistance. Now we are giving it some resistance. Now this is a real battery, not an ideal battery. An ideal battery is a battery with zero internal resistance. So far from grade 10 and grade 11, we're talking about or referring to ideal batteries, batteries whose resistance was negligibly small. But that is not the case in real life. In real life, batteries have got a resistance, which means as the current passes through the battery, it also experiences resistance. As the current flows through the battery, it experiences a resistance. The battery resistance, the internal resistance, as we normally call it. So notice what we're gonna be just roughly demonstrating this. It's a rough demonstration that we're gonna be having. Our battery has got a tiny resistance. What effect does that have? Want to see. So let us build the circuit. Let us build this circuit and let us see. Oh, this is not a nice way of building a circuit. You always need a switch in your circuit. You're always gonna need to have a switch in your circuit. Right, we want to connect now the voltmeter across the battery. When there is no current flowing in your circuit, it says 9 volts. No current flowing in your circuit. No current whatsoever flowing in our circuit. And it's tempting to want to add an ammeter. I think let us add an ammeter. I'm tempted. Anyway, get out of here. Right, let's add an ammeter here. As you can see, there is absolutely no current flowing in your circuit, but there is a reading across the battery. Now, this voltmeter measures the amount of energy stored in the battery per unit charge. When there is no current flowing in your circuit, this is what is stored per unit charge. Lalela carefully, listen carefully. There is no current flowing in your circuit. I think let us add a second voltmeter. But this second voltmeter, we are going to connect it across the bulb. Look at what is happening across your bulb. No current flowing. The bulb is not glowing. The reading on the voltmeter across the bulb is 0. Secondly, no current flowing in the circuit. The reading on the voltmeter across the bulb, the battery or the cell is 9 volts. Now, notice what happens immediately when we close the switch. Immediately when we close the switch, the reading drops from, there is a current flowing in the circuit. The reading drops from 9 volts to 7.5 volts. Let us open our switch again. When there is no current flowing, it's 9. But the moment we drop this, it drops to 7.50, which is the same as the potential difference across the bulb. No current flowing. We have a reading across the battery. Current flowing 0.75. the reading changes. So there are two values that we must speak about here. There are two readings on the voltmeter, especially across the battery. The voltmeter across the battery. I notice that when there is no current flowing in the circuit, I am measuring the what we call EMF. Okay, EMF, we can define this as that reading on a voltmeter across the battery when there is no current. When there is no current flowing in the circuit. So we've got the EMF. Or we can think about this because our battery is a source of energy. So there is a certain energy stored for every 1 coulomb of charge or for every unit charge. It's an energy stored in the battery per unit charge. And then we also saw what we call terminal potential difference. Now, when there is okay, no, let me avoid the voltage, potential difference. This is the 7.5 volts now. This one is the reading on a voltmeter across the battery again. When this time around there is current flowing. And that is a difference there. In one instance, there is a current flowing. In another instance, there is no current flowing, as we have seen there. As we have made the observation, there is current flowing in our circuit. This 7.50 volt is your terminal potential difference. But when there is no current, I don't know what I've done. When there is a current flowing in your circuit, this 9 volts is the EMF of the battery. EMF of the battery. Aha. So the question now is, what has happened to the other amount of energy from 9 volt to 7.5? What has happened to that small 1.5 volts? We must account for that. And how do we account for that? Energy conservation. Remember, at any given point, energy can neither be created nor energy will be destroyed. But instead, energy can be transferred from one point to another point. So I'm having this as my total energy, which is the EMF. So for me to account for this, there must be a certain amount of this somewhere because energy has to be conserved. I cannot destroy this 9 volts. It has to be somewhere, but where is it? And to account for that, remember what we've done. To our battery, we have given a small resistance. Notice that when we drop this to 0, it stays 9. So even when this switch is open, it's 9. When the resistance of the battery is negligibly small or is almost 0, so it's 9 volts without the current flowing. Close the switch, 9 volts with the current flowing because the battery is having no resistance. But the moment we give resistance to our battery, the story changes. So the potential difference must be due to this resistance of the battery. So this other amount of energy must have been used internally within the battery to push the current due to the internal resistance of the battery. And now you'll see that the energy is now conserved. Energy can neither be created nor destroyed. So when you see that the amount of energy that you are starting with You are starting with this amount of energy. How do I account for the lost voltage? I have to provide an explanation, and the explanation comes from exactly doing this. Notice that when the battery is having no resistance, this 9 volts remains 9 volts. But the moment your battery has the internal resistance, the story changes altogether. So it is due to the internal resistance of the battery. That lost voltage, hence we write V internal, because it is what is happening inside the battery, meaning this energy is not effectively available for me to use in the external circuit. It is somehow lost, with inverted commas. It is somehow lost. But energy cannot be lost. No, we can't lose energy. How do you lose energy? It is used inside the battery to drive the current. I hope you guys are with me over there. So this is what we're going to be having, guys. When the battery is having a non-negligible resistance, then that is a difference that we've made. One last time. Switch open, 9 volts. Switch closed, 7.5 volts. The reason for this decline or for this drop in potential difference is due to the resistance of the battery. Due to the resistance of the battery. Let's take some few questions, guys, from yourself. I've been talking a lot. Let's hear any questions. Anyone with a question? Before we get to this. 7 p.m. 7 p.m. Okay, we'll go up until 8 o'clock, guys. The latest that we can stop is 8 o'clock. So I want us to iron this out. Let's play some maths game. Let's play a maths game. In your study of physical sciences, I hope you are seeing that there is a lot of maths that I was doing in between our discussion here. The reason why I'm including this maths is because I need you guys to know that you can never study physical sciences independent of maths. Maths, as it is an abstract subject. It's an abstract concept. Yes, it is very useful. It is very meaningful, but it is too abstract. In math, you just speak about the gradient. But in physical sciences, as we have seen here, a gradient is having a meaning. In this case, for V and I, a gradient represents the resistance of this particular conductor. So we don't just speak of a gradient here. Here, a gradient is a physical quantity. It has meaning. Yet the concept of gradient is taken from mathematics. The first problem that we're going to be solving tonight will speak about the gradient. You will see. You will see when we get to that. Right, ladies and gentlemen, allow me to please say to you, okay, let the internal resistance of a battery we're going to call it small r, small letter r. And then from your definition, it would mean that V internal would be equal to the total current. I don't know what is going on there. This will be equal to the total current, because what passes through the battery is the total current. Let us emphasize that. Multiplied by the smaller nyana resistance. So at the end of the day, I'm going to have EMF is equal to V terminal plus I multiplied by R. This is a total current, bear in mind. But I want to make V terminal the subject of this formula. So I'm going to take IR, which is positive, to this side. Then I want to write it the other way around as R multiplied by I plus EMF. Look at that. Look at it. Okay, let's just write it correctly. V terminal is minus Ri plus EMF. If I look at this close enough, I can always linearize this and have Y is equals to MX plus C. So what does this tell me? It tells me something very important. And this is what we can deduce. If we plot on the y-axis V terminal and on the x-axis the current, we're gonna get a straight line graph with a negative gradient. A straight line graph with a negative gradient, it will look like that. Okay, let us lower this to look like this. That's a straight line with a negative gradient. So what do I notice about that? C being the y-intercept from mathematics. C is the y-intercept. Then this will be the y-intercept. This will be the EMF. And what else do I notice? I notice that this negative R. So from the gradient of the graph, the gradient of this graph that I've just plotted will represent the internal resistance. Y-intercept represents the EMF. So this is what I'm deducing from this graph. And then by comparing these two equations, this is what we can come up with. E gradient of your graph represents internal resistance. Ooh, it's a very meaningful. Internal resistance. And what else do I see? Y-intercept, which is C. The y-intercept of this graph. C is the y-intercept. We know that from mathematics. Represents the EMF. Y corresponds to C. Negative R corresponds to M. So I is your X, the reading of your X values. Y is your reading of your V terminal. And that is precisely what we're going to do. So this is part of your, again, part of your part and parcel of your formal investigation. Determine the internal resistance and the EMF of a battery using the graph. That is what you're going to have to do. Amber physics. So what are these people saying to me? They are simply saying to me that if I've got this kind of a setup where you've got a variable resistor, a variable resistor can be thought of as a, to those of you who are used to the manual radios, the volume of your radio. When you are adjusting the volume of a radio, that is precisely how the variable resistor works. Variable resistor or the rheostat. Let us show you a picture of that. I want to show a picture of a variable resistor. There are different images of this. They come in different forms. Oh, look at them. So as you can see, if you remove the knob of the radio, of the volume of your radio, you'll end up with this, something similar to this, variable resistor. So these are some of your variable resistor. They come in different forms and different shapes. As you can see, there is the knob. You can control this knob. And by changing this, by adjusting this, you are changing the resistance supplied to this, to your circuit. So these are some of the examples. The one that you'll find in most of your laboratories, you'll find this one, this type of your variable resistors. These are some of the types that are typically found in our laboratories. Of course, you can also, in some of your circuits, you can also find, where is this one? The one that will look almost like this. Something like this. Something like that. But they come in different forms and different types and different shapes. So what it is people are saying to me is that if I can take these readings and change and keep adjusting this, keep the battery the same, and adjust the resistance of this bulb and take different readings, something can happen there. So currently I'm having this as 10. So I want to take these readings. And I want us to see if we can come up with this shape of a graph. So we are performing an experiment, guys. We want to determine the internal resistance and as well as the EMF of that battery. So we are collecting the results. We need at least 5. I think 5 will be enough. So I'm going to have a reading here. I'm going to have a current measured in amperes, and I'm going to have the potential difference measured in volts. So reading number 1, 2, 3, 4, and 5. Let us take these readings. We want to take the reading of the ammeter reading as well as the potential, the voltmeter reading. So let us look at that. Currently, with this resistance, the current is 0.75 and the voltage is 7.50. So I'm having 0.75 as well as 7.50. Notice that the units are only written on the heading of each column. So now when you perform an experiment, don't write the units here. Now that's not how we do it in physical sciences. The units are already there. So I'm going to take a second reading by choosing a different value to this one. Let me adjust this and see. See to what? What can we choose? Maybe let's choose 7.5. Check. 2.55. 7 going down. No, let's choose a bigger one. I want to adjust the resistor to something different, 9 ohms. And then I'm taking the reading on the ammeter as well as the potential difference, 0.82, 7.36. But that is pretty close. 7.5 and 7.36, that's pretty close. Let's choose a different value. Let's make it this one. 7.2 and 0.90. Current is 0.90. And this one was 7.20, was it? Yes, 7.2. Let's drop down now to another different resistance. I like this one. 1.00 and 7.00. And then take last 2 readings. We're only taking the readings of the voltmeter. We are performing an experiment, guys. We are performing an experiment. The aim of this experiment is to determine the internal resistance as well as the EMF of the battery that we are using. Let's check when we're at 6.0. Pretty close. Let's make it 5. 1.29 and 6.43. Last reading that we're going to take. Now we're going to plot this graph. We're going to plot this graph. Oh, I can already see it because I'm imagining how these points are looking like. Let's go down to 1.80, 5.4. That's the last. There you go. Look at those. Now, now, ladies and gentlemen, we want to check if we can plot this graph. Let me check if I've got something to the graph plotter. Because I want to cheat my way out of this. So I want to see if I can find something to use to plot this graph. Java Lab, no, chemistry, vision screen. There you go, graphing. So I want to plot these readings, guys. So X, what is on my X? On my X, I'm going to plot the current measured in amperes. And what will be my, on the Y, the dependent variable, I'm going to plot potential difference. Which I'm going to measure in volts. And then I'm going to have my first reading number 1, 0.75 and 7.50. Reading number 2, want to see if we're going to be able to get that same graph, 0.90 and 7.20. Reading number 3, 1.00 and 7.00. Reading number 4, 1.29, 6.43. And the last reading, 1.80 and 5.40. Okay, be done. Look at your readings. So look at your readings, okay? There are your points. I think you can see, I'm not sure if you can see on what is on your screen. Okay, let us say have feet. Not that one. But I think you can see, guys, how your points look like. It's that straight line with a negative gradient. But now, I'm unable to fit this. But this is how a graph will generally look like. Look at these points. I don't see, oh, this one is missing here, 5.40. 1, 2, 3, 4, 5. Look at your points. So you can see that these points are following that trend that we've discussed earlier on, to say that we'll expect a straight line graph with a negative gradient like that one. Look at the shape, look at your points. Look at these points over there. Look at these points over there. They are following a very nice trend. And if you look at it, it looks like they will join all the way up until through that point where this will be your EMF of a battery, which is about, will it be 9 or 10? I'm not sure, but that is what it will look like. So I wanted to show this to you, ladies and gentlemen. So that is how it will look like. When I download this, I want to okay. I don't know why it gives me this vibe. No. Ah, there you go. This is what I wanted. There you go. Look at your graph now. This is what your graph will look like. Save this. So this is what, guys, our graph will look like. Let me import it here. This is what your graph will look like, though it's too big to fit on my screen. Ah, okay, there you go. Perfect. So guys, I hope you are seeing that, what you are trying to be doing here. So whenever we ask you to determine the internal resistance, now we're gonna be getting to that part quickly before we do 1 or 2 questions. So look at your graph, exactly what we have predicted. As you can see, according to this graph, the EMF or the y-intercept here is exactly 9 because it's between 8 and 10. It's 9 volts. All that we need to determine now is calculate the gradient of this graph. And remember, we've said to you, the gradient of such a graph will give us the internal resistance. The y-intercept will give us the EMF. From this graph, what we are noticing is this one. What you already readily notice from this graph is that the y-intercept of your graph, the y-intercept, which represent the EMF, is 9 volts. And the gradient of your graph, oh no, what did I do now? Hey, guys, I don't know what I did. Something just happened and I found myself out. Okay, so all that we have to find now is calculate the gradient. So to calculate the gradient, we select any 2 points that lie on our curve. We can choose any 2 points. This one we can already choose because we know the x value is 0, the y value is 9. And then we can choose another value. Let me check. Do we know this value there? This value over here. It says x value is 2 and y value according to this is 5. So look at this point over there, 5. You've got a 5 there, x value, down there you've got 2, 0. So I've got 2 points, 2 is to 5 and 0 is to 9. Now I can easily calculate the gradient by labeling this x1, y1, x2, y2. So the gradient of my graph will be y2 minus y1, which is 9 minus 5 over x2 minus x1, 0 minus 2. This gives me 4 over negative 2, and then it is negative 2. Remember what we have said. The gradient represents the internal resistance. Therefore, the internal resistance of this battery is equals to 2 ohms. The internal resistance of this battery is 2 ohms and the EMF is 9 volts. Let us verify that. Is that true? Let's go to this and check if this is indeed true. Look at this, the voltmeter across the battery. Let us open the switch. When there is no current flowing, this is the EMF. 9 volts. Does it agree with that? Indeed, it's 9 volts. Internal resistance. What about the internal resistance? Is the internal resistance 2? Let's go and check. It looks like it is 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's definitely 2 over there. So the resistance of a battery is exactly 2 ohms and the EMF of our battery is exactly 9 volts. So we know that this is correct. We have confirmed this experimentally. Now, I don't know if you guys are having any questions because that is basically about the theory that you need. Let us pause, guys. Any questions? Anyone? Somebody? Anybody? All right, if there are no questions, then we shall look at our very first question from your exam papers. This very same question, it deals exactly with what we're doing right now. This very first question, question number 1. Okay. Question number 1. It deals exactly with what we have just discussed. I need the screen capture thing. Number physics. Number physics. Let's look at this question. The very first question addresses exactly what we were just discussing. And then they're saying a group of learners conduct an experiment, and this is their aim. The aim of them is to determine the internal resistance as well as the EMF of the battery. I don't know why I'm unable to use this. Okay, what's going on? Oh, I see. My. To determine the EMF and internal resistance of the battery. This is the aim. The purpose of conducting this experiment, to determine the internal resistance as well as the EMF of a battery. They connected a battery to a rheostat, a variable resistor, a low resistance ammeter, and the high resistance voltmeter is shown in the diagram below. The data obtained from the experiment is displayed in the table. So your variable resistor, like I said, it's like a volume. You can adjust it to a different resistor. Remember, in our case, Tina, what we're doing is we're playing around with the resistance of the bulb. We're playing around with this. And as we change the resistance of the bulb, we're getting different readings of V and I. We're getting different readings of V and I. So this is what it's similar to exactly what they are doing because it's a variable resistor. So that is what they did. And these were their results, voltmeter and ammeter reading. So they go on to now saying to you, state one factor that must be kept constant during this experiment. What did we not touch here, Tina? As I was doing this, look at what I did not touch. I was changing the resistance of the battery, but never did I mess up with the cell or the battery. I was playing around with the resistance of the bulb, but never did I touch the battery. Never did I add the number of cells. Never did I change the potential difference. So once this was changed to this value, I left it like that, and I was only playing around with this. So what I can keep constant is the number of cells in the battery. That is what we should keep constant. Number of cells in a battery. Make sure you don't tamper with this. By keeping the number of cells the same, you are making it a point that the internal resistance and the EMF remain the same throughout. Let me repeat this again. By keeping the number of cells, the cells the same, you are making it a point that the internal resistance as well as the EMF of the battery, they remain the same throughout the experiment. So don't mess around with the number of cells. If you start with 2 cells, continue working with the 2 cells throughout. If you choose to work with 1 cell, continue to work with that 1 cell and do not change it throughout. They want you to, in question 1,1,2, I don't know if you guys are following what I'm trying to explain to you here. So the next question now, we are going to be doing this. Remember, in the first thing that I did, I was using the app to plot this graph. But this time around, they want us using the information table, plot the points and draw a line of best fit on a graph paper. So let us do this manually now. Let us do this manually. But there are certain things that you must take note of as far as graphs are concerned. And for that, I want you to notice something. A graph has got a heading. See, graph has got a heading. And the labels of your graph must be both labeled. Axes are labeled. 1, heading. 2, label the axis before you do anything. Number 3, notice that there is a constant interval on both the y and the x-axis. On the x-axis, the interval is 0,2, 0,2, 0,4, 0,6, 0,8, 1,0, 1, that's a constant interval. Number 3, both your axes, you must choose a suitable interval. Notice on the y-axis, 2, 4, 6, 8, 10. That's a constant interval. So we need the heading, we need the label on your axis. We also need to have a constant interval on both the y and the x-axis before we can do anything. So about your graph, maybe we need to note that down. That when we plot a graph in physical sciences, 1, the graph must have a heading or the title. Secondly, you must label the axis. Thirdly, you must choose the suitable interval. For both x and y axes. So that is exactly what you're going to do. So your heading, it will still be the same as this one. Heading, potential graph of potential difference in volts versus current in amperes. Even if we didn't put the units in the heading, it matters not. But in your axis, potential difference in volts, we include those. Current in amperes, we include the units in the label of your axis. That's a technique, guys. Before we do anything, before you even start worrying about plotting your graph, make sure these 3 critical things are taken care of. I don't know if there are any questions from your side. I want to choose a graph paper so that you can plot this. Guys, any questions from your side? Oh, yeah. Grade small, let's try this one. Oh, so there we have our grade now. We have our grid now and want to do exactly what we are requested to be doing. So want to plot this graph. So I'm going to put in the axes because they are not there. So I'm going to manually put them there manually. So I've got vertical axis. Oh, no. Stop. I've got my vertical axis over here on which I'm going to plot the potential difference, and I've got my horizontal axis over. But don't worry, you will be provided with a graph paper, so you do not have to worry about having to do this. The graph paper will be nicely provided to you. So I wasn't provided the graph paper, so that's why I'm doing this. Right. And then I need to label my axis. Remember, we are plotting the potential difference on the y-axis. You confuse these two, then your graph will be of different meaning. And then we've got your current here measured in amperes. Let us look at these readings. 2, 3, 4, 5, 6, potential difference, the reading on the y values. That one is easy. I know that I'm going to have 1. It has to have a constant interval. 3, 4, 5, and 6. Constant interval. You can't jump from 0 to 2. That's not a constant interval. The moment you start at 2, you must keep that. The next reading will be 6, the next will be 8, the next will be 10. So if you want to jump from 0 to 2, then you must make sure that you continue moving at a constant interval of 2, 4, 6, 8, 10. That's a constant interval. So we are starting from 0, we're moving from 0, 1, 2, 3, 4, 5, 6. So this was easy, and it was easily and nicely taken care of. But with this one, look at this. 0, 0.14, 0, 0.24, 3, 6, 4, 8, 5, 8. And then I can almost see something like 0, 0.12, 12, 24, 36, 48, 60. So that's a constant interval, 0, 0.12, 0, 0.24, 0, 0.36, 0, 0.48, 0, 0.60. That's a constant, 12, 24, 36, 48, 60. That is a constant interval, multiples of 0, 0.12. Multiples of 0, 0.12. That is what we mean by that. So with this, I've got 0, 0.12, 0, 0.24, 0, 0.36, 0, 0.48, and 0, 0.60. This would have been 0, 0.72 if I extended that multiples in the multiples of 0, 0.12. Right, let me plot my first point. So we plot our first point. But before we get there, oh yeah, now let's get straight to that. First point, the 2 is to 0.58. So my first point there is my potential difference 2. 0.58 is pretty close to 0.60. So it will be very close to that. It will be a point somewhere about there. 58 is not 60, but it's pretty close. I hope you guys are following. Next point, 3 is to 0.46. 0.46 is pretty close to 0.48. So it won't be exactly as 0.48. This is 3 over there, but it won't be exactly 0.48. It will be somewhere about there. 46. Somewhere about there. The next one, 4 is to 0.36. That one is precisely on this. This is 0.36. This is 4. It will be exactly there. The next point will be, so you see, you choose a scale that is suitable and easy for you to interpret. 5 is to 0.24. 5 is there, 0.24 is exactly on this line. So there is 0.24, there is 5. It's exactly over there. Last but not least, 6 is to 0.14. 0.14 is just ahead of 0.12. 6 is there. 0.14 will be somewhere about there. And as you can see, look at that, those points. They are tracing a nice linear trend, a very beautiful linear trend. Very beautiful. Look at that. So they said we must draw a line of best fit. So I'm going to try to join this with a straight line. Line of best fit. A line of best fit sometimes may not touch any of the points. A line of best fit may touch some of the points. But you must make it a point that all the points are a fair distance away from the line because they won't fit exactly on the line. So for example, it won't be, oh no, what did I do now? Okay. So I want to now try to make a line of best fit. I don't know why this thing is not allowing me to do that. Oh, I think I know why. Because I didn't select a line. Okay, let's try it now. So look at that. That's your line of best fit over there. The points, they almost nearly fit precisely and nicely on the line. But then we will say to you, for you to get the y-intercept of this graph, let me try to adjust it. For you to get the y-intercept, we then say to you, extend this line until it cuts the x-axis. You see, I've only joined the points. So now I'm going to extend this line. I want to now extend this line so that I can read the y-intercept of this line. So I'm going to try to match this and extend it. So that it cuts the y-axis. So that is what you're gonna do. You then place a ruler, extend your line with a dotted line like I did, and then where the line crosses the y-axis, this is where you are going to get the EMF of your battery. So in my case, this is 6. It looks like 7 comma something because it's slightly above 7. It looks like 7 comma 1 or 7 comma 2, somewhere around there. Somewhere around there. So let me try to check this. It's almost 7,2 or 7,1, 7,1 or 7,2. That is what I'm getting as my EMF, but this will be informed by the next question. Use the graph to determine the following. So from the graph, remember, EMF is equal to the y-intercept of your graph. And then from our graph that we've plotted, it looks like the EMF is somewhere about 7,10. But it must be in volts. And secondly, without using any equation of this form, the internal resistance. So to find the internal resistance, remember what did we say? Calculate the gradient of your graph. Gradient of your graph. So choose any 2 points that lie on your graph. We can choose from here any 2 points that lie on your graph. We can choose from there any 2 points. It matters not really. We can choose, for example, this point and that point. It really matters not which is which. Change in y, here you're going to have 5 minus 3 over change in x, 0,24 subtract 0,46. And that is 2. I don't know what that is. Okay, this doesn't look nice. 0,24, 0,46. So it looks like 2 divided by 0,22. What do we get, guys? Can someone please assist us with the calculator? Oh, this is negative, sorry. What do we get? Negative? Someone with the calculator, please kindly assist.
Negative 9,09.
Negative 9,09. It's a very big value. Sure. Let's check again. Why are we getting such a big value? It's worrisome. Okay, change in y is v over change in x, I. Okay, so it's v over I. And then we're getting, wow, that's a very big value for internal resistance. Therefore, R is equal to 9,09. That's a very big value for the internal resistance, if you ask me. But this is what we got. And that is precisely what you guys will be dealing with when they ask you to use the graph to determine the internal resistance of the battery. So we have started with this virtual experiment that we have conducted, and we obtained our values. And then this theoretical question we did, and we obtained those results. Is this now? Oh, I think I know. Any questions now, guys, before we still have like something We still have roughly 15 minutes before the end of our session. So if there are questions, please feel free. You can use the chat, but you can also open your mic, unmute the mic, and then you can fire your questions away. Any questions? Excuse me. So guys, this is how we go about dealing with this type of questions. Okay. On the lookout for such questions in future. Sometimes the graph will be drawn for you. You'll find some of the questions where in the graph is already drawn. Okay, this is a different story. Let me check if you can find. There, you see here, the points have already been plotted to you. There you have it. So the graph is already drawn for you, so to speak. So the points have already been plotted. All that you have to do is draw a line of best fit. Draw a line of best fit, and then you can easily answer that question. You can easily answer. The questions will follow. As you can see again, 8,1,3. Write down the value of the EMF from the graph. Look at what they have. They've plotted a point over there. 5,1, 5,2, 5,3, it's approximately 5,5. That is the EMF of this battery because they have already positioned a point up there, a point somewhere there, which represents the EMF of your battery. So even when if the graph is plotted for you, be able to interpret. Write down the value of EMF, determine the internal resistance. I think by now you guys have seen how we go about doing this. EMF, you can get that one from calculating the, from the y-intercept of the graph. Internal resistance, you can get that value by calculating the gradient of the graph. So this question 8, I'll send you guys this list of questions. I want you to try that question 8. I need you to try it for me. Can we do that? Can we? And then we're going to end our session in the next 15 minutes. We're going to solve these questions, which is 1,2 we have done. Remember, this is the first part of question 1. The second part of this is question 1,2. Now that is a very more theoretical question, not based on experiment, but those structured questions that we do. Let us finish this off by doing this. Okay, so straightforward question. Three electrical devices, X, Y, and Z, are connected to a 24-volt battery with an internal resistance, R, as shown in the circuit. So we are given the EMF, unknown internal resistance. The power rating of each of the devices, X and Y, are identical. Power rating of X and Y. So if or are indicated, not identical, indicated. Oh, I was so worried. Power rating of each of the devices, X and Y, are indicated in the diagram below. For X, operating maximally at 20 volts, the power rating will be 100 watts. Device Y, power rating is 150 watts. But because, okay, no, let us leave that for later. First question, switch S1 is closed. There is the switch S1. Only switch S1 is closed and S2 is left open, which means this device is not functioning. So I'm only focusing on these two devices. 1,2,1. Calculate the current in X. But before you get to that point, I would advise you that you follow the path of the electric current from the positive terminal you've got the total current. Remember, current flows conventional from the positive to the negative. But the moment you reach this point, a certain portion will go this way. Let's call that Ix, which is what they want us to calculate. And another portion will go this way. Let us call that Iy. So Iy goes and reaches that point. When the two currents intersect at this point, they are combined to give us the total current again. As you can see, the ammeter there measures the rate, which is the total current in your circuit. So these two are connected parallel to one another. Why? Because at the junction where they are connected, there are two alternative paths for the current to flow. Current in, so with that having been said, it should be easy now to look, okay, when I've got a V in resistor X or in device X, I know the potential difference. I also know the power rating. So for your first question, I'm given this as 20 volts. I'm given the power as 100 watts. I'm asked to calculate the current. There is only one formula that can answer this question for you. And that formula is power is equals to V times I, where power in this case is 100 watts. Potential difference is 20 volts, and we do not know the current. But by dividing both sides, we can find that the current here is 5 amperes. And that's it. Having done that, ladies and gentlemen, it should also be easy to see that X and Y are connected parallel to one another. Because they are connected parallel to one another, we have to remember from where we started that we said in a parallel circuit, potential difference is the same. In the parallel circuit, potential difference is the same. So when I see any two devices connected parallel to one another, I have to automatically know that the potential difference of X must be the same as the potential difference of Y. Why? Because the two are connected parallel to one another. And I'm given here, the power rating is 150 watts. They want me to calculate the resistance of Y. Can I do that? Of course I can, because there is only one formula that has got a PV and R, and that formula is power is equals to V squared divided by R. Remember when we were discussing this? There was this formula, V squared divided by R. So power is V squared, but you don't have to worry about that because all of these formula are provided in your formula sheet. So the power here is 150. This is 20 squared, and this is R. So how do I solve for this? Multiply both sides. When you see a denominator, mathematicians will tell you, first multiply both sides by the denominator. This is R. 150R is equals to 20 squared, that is 400. And then we divide both sides by 150. What is 400 divided by 150? Yes, guys, what is 400 divided by 150? 2, what?
2,67.
2,67, thank you. And that's it, straightforward. And then now switch S is closed. So they are saying now we are closing this switch. In other words, we are adding another resistor in parallel. Remember what we have said about adding resistors in parallel. Adding resistors in parallel will increase the total current and decrease the total resistance. That is the effect of adding this. We have already discussed that. So already, before we even answer, we know what is going to happen to the total current. Let's just hear what their first question is. Oh, listen to what they are saying. Identify device Z which, when placed in the position shown, can still enable X and Y to operate as rated. Assume the resistance of all the devices remains unchanged. So which device could that be? When I add to this device, it is not going to change the power rating and the operational readings of X and Y. I can only think of one thing, and that is a fuse. A fuse, the function of a fuse is to protect the components, so that if you've got too high current flowing through your circuit, the fuse will protect the circuit and only the fuse will be destroyed. That's the only device I can think about. So when you add a fuse, you're not going to change the ratings of X and Y, but instead a fuse is to protect these two devices, so that if there is too high current that could otherwise destroy X and Y, it will rather destroy the fuse and protect the components X and Y. That is what a fuse do. I don't know if you guys understood that. It can only be a fuse. Let us speak about that so that we are all on the same path. Function of a fuse in a circuit. Aha, listen to what they are saying there. The fuse breaks the circuit if a fault in an appliance causes too much current to flow. This protects the wiring and the appliance. If something goes wrong, the fuse contains a piece of wire that melts easily. If the current going through the fuse is too great, the wire heats up until it melts and breaks the circuit. So it's definitely has to be a fuse, because all that a fuse does is this protect the wiring and the appliance or appliances. If something goes wrong, it can only be a fuse that will enable these two to still function as rated, but it will protect them. Mm-hmm. Ooh. So to answer their question, how we arrived to this, there is an explanation. The fuse simply breaks the circuit if a fault in an appliance causes too much current to flow. There is your explanation over there. By understanding what is the function of a fuse, by knowing what a fuse does to a circuit, we can easily get to that. So there were people who were guys, I don't know. Some people are struggling with the link. I don't know how we can assist them. But ladies and gentlemen, this is it for tonight. So for tonight, mostly wanted to make sure that we gather enough theoretical explanation, enough mathematical explanation as we can get, so that next time when we meet, we just shoot straight into solving problems concerning to electric circuit, especially the grade 12 aspect, wherein we have now factored in the internal resistance as well as the EMF of the battery. I don't know if there are any questions. I don't know if there are any questions from anyone, because otherwise, from my side, I think this is what I have in store for you tonight. Okay, Sianda is typing. Right, so like I said, we have to apologize to those who joined us later for the Sianda's number. Oh, Sianda, I want us to add you to the WhatsApp group. Okay, Sianda wants to be. I see that most of the people, I see 4 people who have already just joined. 1, 2, 3, 4 using the link. Perhaps I should also do the same for you, Sianda. Let me see if I can get this link quickly. Okay. So please check under the chat, Sianda. I'm trying to get this link for you. Okay, let's check. And anyone who needs to join before you leave this meeting, please click on the link, because otherwise, once you have left, you won't have access to this. So Sianda, if you can quickly, can you see the link under the chat? Please click on it and then quickly add yourself before we depart. As for the rest of us, I'm going to be sending this PDF right now, which I'm already doing. Let me send this as PDF before I forget. Sianda, are you willing to join using the link that I've sent? Okay, we'll keep on checking. So if Sianda. So guys, check the WhatsApp group. I've sent you everything that we have done tonight. It's there already in the WhatsApp group. Sianda, I may have to send it to you separately because you were not. So this is how the document will look like. As you can see, it's already in PDF with my beautiful handwriting. Oh my goodness. Beautiful handwriting. Look at that. So everything that we've covered today, you'll find it there. And this is it for tonight. I'm gonna be sending you guys more questions and a set of questions under electrical circuits, which is a document that I was working with, or rather working on. I will send you the set of these questions. Where is it now? Oh, I've already done that. I sent the questions earlier, but I will send again for the sake of those. So these are different types of questions that we're gonna be working on. These are all the questions that we're gonna be working on. So that is it, ladies and gentlemen. From me, this is what I had in store for you. Let us meet again on Monday. On Monday, we'll start at exactly 6 o'clock. And then we'll be solving this. Hopefully, Mr. Makai will be available, but I will communicate with you on the WhatsApp group if we're going to be having maths. But if Mr. Makai will be available, we'll start from 6 to 7:30. And then at 7:30, we stop. Then Mr. Makai will come in from 7:30, taking you through to 9 o'clock for mathematics. With that having been said, Thank you for tuning in tonight. Let's meet again on Monday, 6 o'clock. We're done. Thank you, guys. Good night.